Welcome to Tech Orbit International. Today, we are conducting an in-depth technical analysis of desktop motherboard voltage sequences. Understanding the exact order in which a motherboard powers up is the most critical skill for any hardware repair technician. We will be using the Gigabyte GA-G31M-S2L as our primary case study to understand the fundamentals before moving into more modern Core i-series architectures. Let's start with the Core 2 Duo G31 motherboard power sequence. Everything begins the moment you connect the ATX power cable. Step 1 is the delivery of the 5 VSB, or 5-volt standby power, to the CO chip, which is an ITE8510TE in this design. Once the CO receives its standby power, Step 2 occurs. It generates the RSMRST signal, or resume reset, and sends it to the Southbridge. This tells the Southbridge that the standby power is stable and ready for the next phase. Step 3 happens when the user presses the power button, sending a PSIN signal to the CO. In Step 4, the CO translates this into a PSOUT signal and sends it to the IC. The IC then responds in Step 5 by releasing the SLP_S3 and SLP_S4 signals back to the CO. These sleep signals act as the green light for the system to fully wake up. Consequently, in Step 6, the CO pulls the PS_on wire of the ATX connector to ground. This triggers the power supply to release the main voltages, including 12 volts, 5 volts, and 3.3 volts. Shown here is Step 7. Now that the main power is flowing, we enter the voltage regulation phase. In Step 8, the 1.8 volts PWM and 1.25 volts regulators start, providing power to the DDR2 RAM slots. Step 9 involves the creation of the VTT_GMCH voltage, which is 1.1 volts. Feeding both the CPU and the MCH Northbridge. Once these voltages are confirmed stable, Step 10 triggers the CO to send the VR_on, or voltage regulator enable, signal to the VRM controller. The VRM section is the heart of the processor's power delivery. As we see in the detailed VRM diagram, the controller takes a 5-volt VCC and 12-volt input to drive the multi-phase MOSFETs. The CPU communicates back via VID signals, telling the VRM exactly how much voltage it needs, usually between 1.0 volt and 1.5 volts. This circuit is capable of delivering high current, often reaching 30 amps. Once the VRM stabilizes this power, it sends out a VRM power good signal back to the IC and CO. This leads to Step 13, where the system clock begins and the CPU_PWR_GD signal is confirmed. Finally, Steps 14 and 15 involve the PLT_reset and CPU_reset signals. This allows the CPU to begin reading the BIOS code, identified here as Step 16. Moving forward to more modern designs, let's examine the Core i-series power sequence. While the logic remains similar, the architecture changes because the Northbridge and Southbridge functions are now combined into a single PCH, or platform controller hub. In these systems, we start with 3 VSB power reaching the CO. The interaction between the CO and PCH involves specific signals like SLP_S3, S4, and S5. Notice that these boards use DDR3 memory and require a VCCSA voltage and a specialized 1.05 volt VTT_PCH rail. In the I-series sequence, the VRM controller uses SVID, or serial voltage identification, for high-speed communication with the CPU. You will also see additional signals like VR_ready and PCH_PWROK. These ensure that the PCH and CPU are perfectly synchronized before the PCH releases the PLT-RST, or platform reset, which is the final gate before the system can boot. Welcome to this technical overview of desktop motherboard architecture. Today, we are analyzing the secondary power supply circuits on the Gigabyte H61M motherboard, specifically focusing on the 5V and 3V dual rails. To understand this board, we must look at the relationship between the physical components and the power sequence. On the screen, you can see the physical motherboard on the left, and its corresponding power sequence block diagram on the right. Let's begin with the concept of dual voltage. In a desktop system, we have standby voltage, which is present as soon as the power supply is plugged in, and main voltage, which activates after the power button is pressed. The dual circuit is responsible for intelligently switching between these states to ensure continuous power delivery to critical chips. Please direct your attention to the schematic diagram on the right. The process begins at step 1, with the 5V standby coming from the ATX power connector. At step 2, highlighted in the red box, a MOSFET converts this source into 5V dual. Immediately following this, at step 3, the voltage is regulated down to generate the 3V dual rail. Now, follow the red arrows connecting the diagram to the motherboard image. These arrows point to the specific MOSFETs responsible for this conversion. These transistors are physically located near the PCI slots in the bottom edge of the board. For repair technicians, this area is critical. If a motherboard appears dead, the fault often lies here. If the 3V dual rail is missing due to a faulty MOSFET, the PCH and the ITE Super I/O chip will not receive power, and the system will fail to start. By verifying the voltage at these specific points first, you can diagnose no power issues much more efficiently. On motherboards like the H61MD2B3, these dual voltages are managed by specific MOSFETs. The 5VDUAL and 3VDUAL rails allow the motherboard to maintain certain functions, like wake on LAN or maintaining CMOS settings, even when the system is in a deep sleep state. If you are troubleshooting a board that won't trigger at all, checking these FETs and the standby rails is a priority. In summary, diagnosing a motherboard requires following this exact trail of signals. If you have 5 VSB but no RSMRST, the CO might be faulty. If you have power but no CPU_reset, your VRM or clock generator could be the culprit. Thank you for joining this deep dive at Tech Orbit International. Mastering these sequences is what separates a professional technician from a hobbyist. Stay tuned for our next session where we will perform live measurements on these circuits.